Good evening, Lamai. Today we are going to discuss about the real gases, right? So far we had introduced you the ideal gases, the ideal gas equation and the stuff, right? How they behave. And today onwards we are going to discuss about the behavior of real gases, right? So when it comes to higher temperatures and low pressures, yes, real gases tends to behave like ideal. But when it comes to the other pressures and temperatures, that means with the high pressures as well as the low temperatures, they deviate from the ideal behavior. Right? First, let's discuss why they will deviate from the ideal behavior when we are referring to the low temperatures and the high pressures. First concern that thing, right? After that, we can discuss why real gases tends to behave ideally when a high temperature and low pressure is applied, right? So first of all, let's discuss why these guys, the real gases, tends to behave ideally. First of all, so what are real gases, right? I forgot to tell you, right? The real gases are the day-to-day gases, right? So the N2 gas, O2 gas, even the CO2, H2, any gas you know, right, comes under the real gases, right? Okay, let's discuss why they are not considered as ideal gases, right? The thing is like this. So if you have to examine a real gas, right? So let's say this is your vessel, right, containing some real gas, say O2 gas. So they are actually real gas molecules are with kind of a volume, right? Not like the ideal gases, those are with kind of a volume, right? Real gas molecules are with some volume, right? Real gas molecules are with considerable volume. So, compared to the volume or space occupied by real gas molecules, compared to the total volume of the vessel, the volume occupied by the real gas molecule is not negligible now, as these guys are with some volume, right? Compared to the volume of the vessel, right? The volume occupied by these guys, the space occupied by these guys can't be neglected. Can't be neglected. So if you are to take all of these guys to a corner, right, those 5 molecules will take this kind of a space, right? So compared to the volume of the vessel, you can't neglect this volume, right, occupied by the real gas molecules, right, as those guys are with a volume. But when it comes to ideal thing, what is the nature there with the ideal gases? So as those guys are point masses like this, compared to the volume of the vessel, the volume occupied by the gas molecules, if you were to take all of these guys this corner, right, that is negligible. This volume is negligible compared to the volume of the vessel, right? That is what happens with the ideal gas. This is what happens with the real gas, right? So we can't consider these real gases as ideal gases, as those guys are with some considerable volume, right? That is one factor, one reason for real gases to not to, right, consider as ideal gases, right? Let's discuss about the second reason, right? So then the second reason is actually, as real gases are with some size, right, not like in ideal gases, right, these molecules, real gas molecules, feel the existence of the other molecules. This guy feel the existence of the other guys, right? So that attractions and the repulsions may occur. So these guys will, this one, let's say this one will attract to this one, or if they are very much closer, this guy will repel from the others. So attractions and repulsions will be there with real gas molecules, as those guys feel the existence of the other gas molecules. But when it comes to ideal gases, see, these are very small, and the distance between them is very large compared to their sizes. The distance between them is very huge. So this guy won't feel the existence of the other particles, other gas molecules. So attractions and repulsions are not possible with ideal gas molecules. But when it comes to real gases, yes, they will attract as well as repel, because the molecules feel the existence of the other guys, right? So because of these two facts, right, so real gases are not considered as ideal gases. No, these guys are behaving, right, differently to the ideal gases, right? Okay, those are the major two facts, right? Right. Let's concern how a real gas is possible to behave ideally when the temperature is very high and the pressure is very low. Let's discuss about that thing, right? Even though real gases are deviating from the ideal behavior at low pressures and high temperatures, yes, they will behave ideally. The real gases tends to behave ideally. Let's discuss why is that, right? It is like this, Lama. Let's consider first about the low pressure situation. This is kind of a low pressure situation, right? Let's consider about low pressure and high pressure situations, right? So we know for the gases, P is equal to CRT. P is equal to CRT, right? That means if you are concerning a constant temperature, R is always a constant, P is proportional to C. This means pressure is a measure of concentration. Pressure is a measure of concentration, right? So when the concentration is high, pressure is high. When the concentration is low, pressure is low. What is this concentration? Concentration means actually it's a measure of molecules in a unit volume. It's a measure of molecules in a number of molecules in a unit volume. If you have more number of molecules in unit volume, higher the concentration. If you have a less number of molecules in unit volume, lower the concentration, right? So one can say the pressure is a measure of number of molecules in unit volume, right? Okay. See how we can use this thing to confirm that the pressure, the real gases will behave ideally when the pressure is very low. It's like this, Raman. So let's concern two systems, right? So this is one system, right? When the volume is very low, but you have, let's say, 5 particles. These are real gas particles. Real gas particles, right? So in a volume you have 5 particles. Volume is very low. Volume is very low. That means your N over V is, volume low means N over V value is high. That means your concentration is high. That means your pressure is high. This represents a system with very high pressure with some real gases. Let's concern the same 5 molecules appearing in this large volume. Same 5 molecules appearing in this large volume. See, the guys are like this. Same 5 molecules appearing in this large volume, right? So here, right, your volume is very high, right? That means in OV, number of molecules in unit volume is very low. That means concentration is very low. That means pressure is very low. Let's compare these two systems. A system with very high pressure and system with very low pressure. Right? You clearly see, right? These particles are very close to each other, while these particles are very far away from each other. Here, compared to the volume of the vessels, the space taken by the gas particles can't be neglected. Some considered space is taken by the gas particles. This is referred to as the non-ideal nature. But when it comes to this one, compared to the volume of the vessel, very large volume is there, right? The space taken by these gas molecules can be neglected, actually negligible, right? The same 5 gas molecules like here, right? So if you are to put these all the guys to this corner, that space is negligible compared to the space of the vessel, right? So that is the ideal behavior, ideal nature, right? Ideal nature. Compared to the volume of the vessel, the volume occupied by gas molecules is negligible, right? That thing will happen when the pressure is very low. Real gas molecules also tends to behave ideally. The volume factor, that is how they are addressed, right? Okay. The other thing is, as these guys are very far away from each other, no attractions or repulsions would occur among these particles. But not here. The particles are very close. Attractions and repulsions will occur. But here, the particles are very far away from each other. Compared to the distance between them, their size is negligible, so that these particles won't feel the existence of the other particles, so that they can't get attracted or they can't get repelled, because these guys won't feel the existence of the other guys, right? So that at these very low pressures, these guys tends to behave ideally. No intermolecular attractions or no repulsions, or the volume can be negligible of a molecule compared to the total volume of the gas, the ideal behavior, right? So even the real gases will follow the ideal nature when the pressure is very low, right now. And what about the temperature, Lamai? What about the temperature fit? Right, I earlier said that with very high temperatures, yes, they will follow the ideal behavior, even the real gases, right? How come? The point is Islamite. The point is, right, when the temperature is very high, right, the particles will move with very high speeds. Why is that? Last day we had discussed that the temperature is a measure of kinetic energy. Right? We had proved that thing last day, right? The average temperature only depending on the kinetic energy. The average kinetic energy only depends on the temperature, right? No? Okay, so the temperature is a measure of kinetic energy. So higher the temperature means higher your kinetic energy is. That means your particles will move with high speeds when the temperature is high. The same particle, no? Same mass is there, but the half m squared is high with a high temperature. That means the velocity is the one, it should be higher at that point, right? So high temperatures means high kinetic energies. So that means the particles are moving very speedy motions are there among particles, right? Then let's discuss about such kind of system, right? When the particles move very fast what will happen? So it is like this, Lama. Let's concern two systems where particle movements are very slow and the particle movements are very high. Right? See. So if you are with two systems, right, where temperature is very low here and temperature is very high here. Temperature is high and temperature is low. So these are the real gas molecules. Right? These are the real gas molecules. Right? Temperature is high means their kinetic energies are high. Temperature is high means their kinetic energies are high. Temperature is low means their kinetic energies are low. Right? So when the kinetic energies are low, it's like these guys are moving with very slow speeds, right? These guys are moving with very slow speed, like this. Let's say these guys are coming, let's say, coming face to face, right? With very slow speeds. Say this is 2 ms minus 1. This is just 3 ms minus 1. Very slow speeds. But here, the guys are passing with very high speeds. Say 200 ms minus 1. Very high speed. 300 ms minus 1. Right? Very high speeds. See, then what will happen? Then what will happen? Right? So think of this kind of process. මේ වගේ දෙයක් ගැන පොඩ්ඩක් හිතන්න ළමයි. හරිද? දැන් හිතන්න you and your friend, right? ඔයා ඉන්නවා, ඔයාගේ යාළුවා ඉන්නවා. හිතන්න highway එකේ යනවා. හරි? දැන් දෙන්නම හිමින් යන්නේ. හරිද? ඔයත් හිමින් යනවා. ඔයාගේ යාළුවා අර පැත්තේ ඉඳගෙන හිමින් එනවා. හරි? traveling with small speeds. හරි? ඔයා හිමින් එනවා මෙහෙම. අර පැත්තේ යාළුවා හිමින් එනවා. හරි? ඒතර ඔයාලා පේනවා දැන්. දැන් ඈත ඉඳන් ඔයාලා පේනවා අන්න ඔයාගේ යාළුවා එනවා. Your friend is coming. Right? Then you can say hi. Right? Even your friend can say hi because both of you see each other. ඔය දෙන්නම දකිනවා. මොකද ඔය දෙන්න හිමින් එන්නේ. හිමින් එනකොට ඔය අර වාගේ යාළුවා ඈතින් එනවා. ඔයාට පේනවා. ඒතකොට ඔයාලා hi කියන්න පුළුවන්. Hi means it's kind of an attraction. Hi. Attraction. Right? When passing by, you can say bye as well. The හිමින් pass වෙන්නේ. හිමින් pass වෙන්නේ දෙන්න. Slowly pass වෙන්නේ. ඒතකොට ඔයාලා bye කියන්නත් පුළුවන්. Hi, bye. You can say. Right? So attractions are possible when the things are traveling with smaller speeds. මේ හිමින් යන්නේ නේද? හරි. අර ෆිට් එකක් දාන්නත් පුළුවන් නේ. පහක් දාලා යන්නත් පුළුවන් වාට. හිමින් යන්නේ. හරි. හිතන්න ඔයා ඉන්න. ඔයාගේ යාළුවෝ ඉන්න. යාළුවා නෙමෙයි. ඔයාගේ සතුරෙක් ඉන්නවා කියලා දන්න. Your enemies there. ලොකුම තරහකාරයෙ ඉන්න. හරි. ඈතින් එනවා. හරි. දකින්න තරහකාරයා. මොකද කියන්න පුළුවන්? ඔයාට මොනවා හරි එයාට කියන්න හොඳ ටිකක් මතක් කරගන්නත් පුළුවන්. ඕන්නම් බනින්නත් පුළුවන්. හරි. යද්දි පාස් වෙද්දිත් බයිනවා. හරිද? So repulsions would occur. Repel වෙන්නත් පුළුවන්. You can say hi and byes, attractions. Right? You can say some opposite words as well, repulsions, right? So attractions and repulsions are possible when the particles are traveling with slow speeds. That is what happens when the temperature is low. When the temperature is low, kinetic energies are low. That means particles are traveling with small speeds. That means attractions as well as repulsions are possible. Right? Non-ideal behavior. Non-ideal behavior. Attractions, repulsions possible. What about this situation? මේ ගැන පොඩ්ඩක් හිතන්න. දැන් ඔයා ඉන්නවා. ඔයාගේ යාළුවා එනවා. හැබැයි දෙන්නම travel කරන්නේ very high speeds වලින්. ඔයා 200 ms minus 1 නැත්නම් h minus 1 වලින් යනවා. අරයා 300න් එනවා. ඔයා 200න් යනවා. right? මොකද වෙන්නේ? ඔයාට බේනවා ඔයාගේ යාළුවා වෙනවා. hi කියන හ කියනකොටම පාස් වෙලා ඉවරයි. හායි කියන්නේ හිතනකොටම ඔයාගේ ඇලුව පාස් වෙලා හුඟක් දුරට ගිහිල්ලත් ඉවරයි. Attractions are not possible. ඔයාගේ enemy එනවා. හොඳට කියන්න දෙකක් මතක් කරගන්නකොට ඔයා පාස් වෙලත් ඉවරයි. හරි? කියන්න දෙයක් මතක් කරගන්න ඔයා පාස් වෙලත් ඉවරයි because you as well as your enemy or friend, the guys are traveling with very high speeds. No interaction time. Very less interaction time or no interaction time when the particles are traveling with high speeds. No or less interaction time means attractions and repulsions are not possible. You can't attract or you can't get repelled as no interaction time is there. දෙන්නම අර හයියෙන් පාස් වෙන ඉච්චරයි. attract වෙන්නවත් repel වෙන්නවත් වෙලාවක් නැහැ. Right? That is the idea. So when the temperature is very high, that is what happens. The kinetic energies of particles are very high, so that very minimum interaction time, no interaction time. So attractions and repulsions are not possible with this kind of system. So that is the ideal behavior. No intermolecular attractions, no repulsions among gas particles. Right? This is the ideal behavior. Right now? So at very high temperatures, yes, even the real gases, right, tends to behave ideally. Even the real gases tends to behave ideally. Got the idea? In other temperatures as well as other pressures, in low temperatures as well as in high pressures, they are not behaving ideally. The thing is clear? Right. Just go to the note quickly, what they are saying there, right? At the page number 18, it is said, right? Even if the low pressures and high temperatures are favorable conditions for the ideal behavior of real gases, in other conditions, real gases do not behave ideally, and hence, for real gases, PV is not equal to nRT, right? If the low pressure is high or temperature is low, real gases not tend to behave ideally, so that they are not following the ideal gas law. They are not following the Peiko's nRT. So for real gases in those situations, PV is not equal to nRT. Got it? Right. Because of, they are saying the two reasons why the real gas is not following the ideal behavior. The two reasons are the existence of intermolecular forces among real gas molecules, and secondly, it says, as real gas molecules are not point masses, the volume of real gas molecules cannot be neglected compared to the volume of the gas. The idea is clear? So those are the two reasons for real gases not to follow, right, the ideal gases, not to behave as ideal gases in low pressures, low temperatures and high pressures. Right now? Okay, the idea is clear now about the real gases? Right. After this, now we are going to discuss about some amendments. Some amendments we can think of real gases. Some amendments we can think of to do to the ideal gas law for the real gases. Right? Let's discuss about that thing. As we know that now the real gases are not following the Peiko's nRT, we have to think of some new equation of state for real gases, right? So we have to discuss about that thing, right? That will be studied in the form of Van der Waals equation, right? The new equation for real gases will be introduced as Van der Waals equation, but not now at the latter stage of this lesson, right? First of all, let's discuss the deviation, how to measure the deviation of real gases from the ideal behavior. How much deviate? Not all the real gases will deviate with the same value from the ideal behavior, right? So some real gases are very close to ideal gases and some are very away from the ideal behavior, right? So let's discuss to measure, a way to measure the ideal behavior, right? To way to measure the deviation from the ideal behavior for the real gases. Let's just talk about that thing, right? So for that, we use the help of the compressive factor. So the first subtopic we are going to learn today is the concepts of compressibility factor, right? Okay, let's come up with that. Compressibility factor. Compressibility factor, right? It is normally symbolized with Z, capital Z. Compressibility factor, right? Okay, what is this, right? Let's discuss about the definition. So compressive factor is this ratio for any considering real gas, right? For any considering gas, the PVM over RT, this ratio is considered as the compressive factor of that considering gas. The ratio of PVM over RT is referred to as the compressive factor of a considering real gas, right? So this is the compressive factor. Right? And the P, R and T are with the normal meanings, right? So P is the pressure of the gas, R is the universal gas constant, and T is the temperature of the gas. And this Vm, this is special. This Vm is not just the volume. This Vm is not just the volume. Right? This Vm is actually volume occupied by 1 mole of gas molecules. The space occupied by 1 mole of gas molecules. Or one can say volume of 1 mole of gas molecules. Volume of 1 mole of gas molecules is referred to as the compressive factor. Sorry, referred to as the Vm. Right? Volume of 1 mole of gas molecules is referred to as the Vm. Right? In other words, it is referred to as the molar volume. Molar volume. Molar volume. So Vm is the molar volume, or one can say volume of 1 mole of gas molecules. Not just the volume of the gas, but it is the volume of 1 mole of gas molecules. Right? So this is the first definition of the compressibility factor. The PVM over RT ratio. That is the compressibility factor for any considering gas. Right? Vm is special. It is the volume of 1 mole of gas molecules. Right? That means it is the molar volume. Right? Okay. The idea is clear. Right. So if you think of ideal gases, this Z value is going to be 1. Z value is going to be 1. How come? See, it's like this now. For ideal gases, we know that PV is equal to nRT. No? For ideal gases, the PV is equal to nRT. No? Right? If you are to take this N to here, PV over N is equal to RT. Then V over N means volume of 1 mole of gas molecules. Volume per mole. Volume per mole. Volume of 1 mole of gas molecules. That is Vm. Molar volume. Volume per mole. Volume of 1 mole of gas molecules is equal to RT. See, for ideal gases, PVM is equal to RT. So if you are to consider the Z, the compressive factor Z, as we know, the Z is equal to PVM over RT. As Vm is equal to RT, those can be cut off, right? So that Z is equal to 1. As Vm is equal to RT, right? these two guys are with the same value, so ultimately Z will get the number 1. So for ideal gases, the compressive factor is equal to 1, right? Compressive factor is equal to 1. The idea is clear, right? That is about the ideal gases and its compressive factor, right? Okay. So this is the first definition, right? Actually, this is the first definition of compressive factor. The ratio of PVM over RT is the compressive factor for any considering gas, right? In your resource book, another definition is given. In your resource book, another definition is given. Let's discuss about that second definition of compressive factor. Second definition. Right? See, what is that? It's like this now. Right? As we know, right? dZ is equal to PVM over RT. If you consider some real gas, you can write like this. Let's consider gas A. Instead of gas A, or the real gas, let's say consider instead of real gas. So instead of real gas is going to be equal to PVM, molar volume of that real gas, divided by the RT. No worries, no? For considering real gas, compressive factor is the PVM of that real gas, molar volume of that real gas over RT. But we know for ideal gases, we know that PVM for ideal gases is equal to RT. PVM for ideal gases is equal to RT. We had, right, confirmed that in earlier, right? For ideal gases, molar volume of ideal gas into P is equal to RT, right? Then we can substitute this into here. Instead of RT, we can write this value. Instead of RT, we can write this thing, right? So that you have the PVM real. Instead of RT, instead of this RT, you write this. Same RT, you write this. That is PVM of ideal gas, right? As P's will cancel off like this, so this will be equal to VM real over VM ideal. Right? So I'll take the final conclusion. So one can say, is it of a real gas or considering gas is equal to molar volume of that gas, considering gas, divided by molar volume of that gas if it behaves ideally. If it behaves ideally at the same temperature and pressure. At the same pressure, it should be the same pressure as well as the same temperature. At the same temperature and pressure. Right? So that is the second definition of compressive factor. Second definition. Right? What is the definition? The compressive factor of a considering gas is equal to molar volume of that gas, molar volume of that considering gas divided by the molar volume of that gas if it behaves ideally at the same temperature and pressure. The same temperature and pressure. Right? That is the second definition. Right? We came up with two definitions for the compressive factor. The first thing is compressive factor of a given gas is the ratio of PVM over RT. That value is referred to as the compressive factor of a given gas. The second definition is compressive factor of a given gas is the molar volume of that gas divided by molar volume of that gas if it behaves ideally at same temperature and pressure. Right? Those are the two definitions for the compressive factor given in your resource book. Right? Okay, let's go to the note and see what they are saying there. Right, the compressive factor, it says for any gas, ideal or real, right, the quantity PVM over RT is called compressibility factor, and it is used as one of the measures of the deviation of real gases from ideal behavior. Right, deviation of real gases from ideal behavior. Right, the compressibility is given is it is equal to PVM over RT, where the Vm is the molar volume, that is a volume of 1 mole of molecules. Right. The second point, it says at the next page, right, in other words, the compressive factor is the ratio of actual molar volume, the ratio of actual molar volume of the gas, the ratio of actual molar volume of the gas to molar volume of it if it behaves ideally at the same temperature and pressure. If it behaves ideally, if it behaves as an ideal gas at the same temperature and pressure, right? So that is the second definition, and they have proved that thing. This derivation has been done, right now. Okay, and finally it is said that when considering an ideal gas, the compressive factor is 1. When considering an ideal gas, the compressive factor is equal to 1. That is clear, no? We had derived that thing as well, right? Those are things that you're not, right? You should be able to derive this thing, right? Where the compressive factor is equal to Vm over real or Vm RT, Vm over ideal, right? Vm real over Vm ideal, right? That should be thing could be derived, right? You should be able to derive that thing, right? No? Okay. So that is about the introduction of the compressive factor, right? Now let's discuss what are the factors affecting this compressive factor of a gas, right? The two factors which affect the compressive factor, right? Let's discuss about those things, right? Actually, there are two factors which affect the compressive factor. Those are the temperature and pressure, or one can say temperature and kind of gas. Temperature and kind of gas, right? So if your gas molecules are with strong attractions, it will affect to the pressure, right? It will affect to your pressure of the gas. So pressure is a measure of kind of gas, or kind of gas is kind of a measure of pressure, right? Okay, so the two things affect the compressive factor is actually pressure or the kind of gas. That is one factor. The second factor is the temperature. We'll discuss the relationship between the pressure and the kind of gas, right? Okay, right. So now we are to factors affecting the compressive factor. The first factor we are going to discuss here is the kind of gas, right? Kind of gas. This is how it will affect the compressive factor. Kind of gas, right? Okay, so let's discuss at low pressures and at high pressures how the compressive factor will be affected by the kind of gas, or by the presence of the intermolecular interactions of those gases. So when the gas varies, the intermolecular interactions will vary, right? That is what referred here, right? So one can say the kind of gas or intermolecular interactions. Right? Okay, the first thing is this. Let's discuss about the low pressure situations. So the low pressure situations. at low pressures, right? So it's like this now. So at low pressures, right? At low pressures, right? Think of this kind of system. So let's say if your gas is ideal, if your gas is behaving ideally, if your gas is ideal, right? This should be the picture. So 5 gas molecules are there behaving ideally. No attractions or repulsions among gas molecules. No attractions or repulsions among gas molecules if your gas is ideal, right? So that the volume occupied by these gas molecules is referred to as the volume of the ideal gas. Volume of the ideal gas, right? Let's consider these 5 dots represent 1 mole of gas molecules. Let's consider these 5 dots represent the 1 mole of gas molecules. If so, this volume of this stuff is going to be the molar volume occupied by 1 mole of gas molecules. So we can denote this thing as molar volume of the ideal gas. So this is the ideal situation, right? The point masses, no attraction repulsions among particles, the ideal behavior. So the volume occupied by 1 mole of gas molecules is referred to as the molar volume. Molar volume is the ideal situation, right? Then when it comes to real gases, if these guys represent a real gas, then if these guys represent a real gas, then right, these gas particles are with some volume like this, some volume like this, right? So they feel, these gas molecules feel the presence of other molecules. They feel the presence of other molecules, so that intermolecular attractions are possible. Intermolecular attractions are possible, as well as intermolecular repulsions are possible, right? Intermolecular interactions are possible when these are real gas molecules. Let's discuss what kind of interactions possible when you are dealing with low pressures. What kind of interactions? Whether the attraction interactions or the repulsion interactions are possible with low pressures. Let's concern about this thing, right? So let's consider here, right? So low pressures means, right, the particles are close to each other. Low pressures means the particles are close to each other. Low pressures means particles are away from each other. Low pressures means particles are away from each other. Why? Low pressure means concentration is low, right? P is proportional to concentration, right? Low pressures means concentration is small, so that particles are bit away from each other. Particles are bit away from each other. So it's better to represent this low pressure situation with some greater volume, no? So this is the low pressure situation, right? Particles are bit away from each other. Low pressures, no? Right? So Lamai, when the particles are away from each other, the attractions will predominate. The attractive forces will predominate. When the particles are bit away from each other, the attraction forces will more pronounced than the repulsive forces. Why is that? ඇයි එම් වෙන්නේ? පොඩ්ඩක් මෙහෙම හිතලා නමයි. හරිද? දැන් හිතන්න this is a normal scenario, right? It's very same to our human beings. අපි වගේම තමයි මේගොල්ලෝ. හරි. හරි. මේ හිතන්න පොඩ්ඩක්. දැන් ඔයා මෙතන ඉන්නවා. හරි. දැන් ඔයා මෙතන ඉන්නවා. හරිද? දැන් ඒතකොට අර වාගේ අර ඈතින් හිතන්නකෝ ඕගොල්ලෝගේ අර ගෙදර පොඩ්ඩක් ගීට්ටු වලට ඈතින් වගේ. හරි. කවුරු හරි හොඳ ඇක්ට්‍රස් කෙනෙක් ඉන්නවා. හරි. දැන් ඔය ටීවී ඩ්‍රාමා වල ඉන්න ඇක්ට්‍රස් කෙනෙක් ඉන්නවා කියලා. හරි. මට මතක් වෙන්නේ නැහැ නමක් ළමයි මේ. හරි. දැන් මොකක් කරනවා? ශල්නි තාරකා ඉන්නවා. හරි. ශල්නි තාරකා ඉන්න ඕගොල්ලෝ ගෙදර ළඟ. ගේට්ටු ළඟ. හරි. ටික ඈතින් ඉන්නද? ළඟින් නෙමෙයි ඉන්නේ. ඈතින්. රයිට්. දැන් මොකද වෙන්නේ? හරි. අන්න තාරකා ඉන්නවා ඈතින්. හරි. දැන් මම මෙතන ඉන්නවා. හරි. මොකද වෙන්නේ? You will attract to her. ඔයා යාට attract වෙනවා. ලස්සනට පේනවා. ලස්සනට ඉන්නවා. හරි. ලස්සනට ඉන්නකොට ඔයා මොකද වෙන්නේ? ඔයා attract වෙනවා. හරිද? දැන් ඔයා මේ මීඩියා. හරි. you තොරනේ තාරකා ඉන්නවා. හරි. ඈතින් ඉන්නේ. තාරකා ඉන්නෝ. හරි. ඈතින් ඉන්නේ මොකද වෙන්නේ එතකොට? ඔයා ඇට්‍රැක්ට් වෙනවා. ඔයා ළඟට එනවා. හරි? ඔයා ළඟට එනවා. ඔයත් පොඩ්ඩක් අදින් ළඟයි ළඟ ඉන්නේ නේද? තාරකත් ඇට්‍රැක්ට් වෙනවා. වන්නේ හරි. දැන් ඔන්න attractions. Attractions will occur when two guys are with some distance. දෙන්න ටික ඈතින් ඉන්නවනේ attractions තමයි වෙන්නේ. හරිද? right. දැන් ඉතින් දෙන්න ඇට්‍රැක්ට් වෙනවා දෙන්න. හරි. දැන් මොකද ලඟ වෙනවා. ලඟ වෙනවා. ලං වෙලා see දැන් මම මෙච්චර ලං වුණා. හරි. තාමත් ඇට්‍රැක්ෂන් තමයි වෙන්නේ. හරි. තාම ඇට්‍රැක්ට් වෙනවා. ලං වෙනවා. හරි. හොඳටම ලං වුණොත් මොකද වෙන්නේ ළමයි? මේ හරියට ලං වුණොත් හරි. දැන් මොකද වෙන්නේ? When the particles are very very close to each other, what will happen? In this position, it is attraction, right? When the particles are with some distance, attractions will be. When the guys are very very close to each other, what will happen? Now you see the defects on her face. හරිද? දැන් තාරකාට ඇට්‍රැක්ට් ලා දින ළඟටම වෙලා දින මේ වාග ළඟට ආවොත් මොකද වෙන්නේ? ඔයාලා දැන් තාරකාගේ දින ඔක්කොම ඩිෆෙක්ට්ස් ටික වෙන්න පටන් ගන්නවා. හරි. අර ලස්සනට ඈතට බිවුනට ලස්සනට. හරි. ළඟට ආවොත් මොකද වෙන්නේ? ඔයාලා වෙන අර මූණේ දින නේද ඔක්කොම ටික වෙන්න පටන් ගන්නවා. හරි. හරි. අර වලවල් ටිකයි ඔක්කොම බීන විදිහට. අර මේකප් තට්ටු දාලා වහපු ඔක්කොම ටික පේන්න පටන් ගන්නවා ළඟටම ආවට පස්සේ. හරිද? ඉතින් පස්සේ ළමයි තව ඇට්‍රැක්ට් වෙන්නේ නැහැ නේ. හරි. ඉතින් පස්සේ නිකන් අර ලස්සනට හිටපු තාරකා නිකන් දෙවඟනක් වගේ හිටපු තාරකාව දැන් ඔයාලට වෙන්නේ නිකන් නේද? හරි නිකන් වාර නේද? හරි මොහොනී වගේ වෙන්න පටන් ගන්නවා. රයිට්. ඕකේ. ඒතර එච්චරනේ අවුල් නිකන් හරි. කොහොම මේකප් තට්ටු කො වෙන්න පටන් ගත්තා. හරි බය වෙලා ටක් ගාලා මොකද වෙන්නේ? ඔයා රිපෙල් වෙනවා ඉතින් අනිවාර්යෙන් රිපෙල් වෙනවා. ළඟටම ආවට පස්සේ හරි. යථා ස්වරූපේ තේරුම් ගත්තා රිපෙල් වෙනවා. තාරකත් දින් රිපෙල් වෙනවා. ඉතින් ආයෙත් නේද? ඔයා ළඟට ආවා කියන්නේ තාරකා ළඟින් ඉන්නනේ. හරි ඌත් රිපෙල් වෙනවා. හරි. අනිවාර්යෙන්. හරි. ඔච්චර ක්ලෝස් වුණාට පස්සේ මොකද වෙන්නේ? Repulsions will predominate. Repulsions. That is what happens. Right? When you guys are away from each other, but you see, when you guys see, but you are away from each other, the attractions will predominate. When you are much closer to each other, very close to each other, definitely repulsions will happen. Repulsion forces will predominate. More pronounced. That is the normal age. සාමාන්‍යයෙන් තමයි කියන්නේ ළමයි ඇට්‍රැක්ට් වුණාට කමක් නැහැ. එක්තරා මට්ටමකට විතරක් ඇට්‍රැක්ට් වෙන්න කියලා. මට්ටමකට ඇට්‍රැක්ට් වෙනවා ඇති. ඊට වඩා ඇට්‍රැක්ට් වෙන්න යන්නේ වාගේ එලිම රිපෙල් වෙනවා තමයි ඉතින්. හරි. ඉතින් මේකේ මිනිස්සුන්ට අදාළයි. හරිද? ඇට්‍රැක්ට් වෙනවා එක්තරා මට්ටමකට විතරක් ඇට්‍රැක්ට් වෙන්නේ. දැන් ඔය දින ළමයි සාමාන්‍යයෙන් ඔය දින ඔය ඕගොල්ලෝ උන් තරම් අහලා නේද? හරි හොඳට යාළු වෙලා හොඳට ඉඳලා. හරි කසාද වෙන්දර පස්සේ මොකද වෙන්නේ? සමහර කට්ටිය අහලා නේද? අවුරුද්දයි මාස දෙකයි මාස තුනයි කෙලින්ම ඩිවෝස් වෙනවා. ඇයි ඒ? අර ඈතින් ඉන්නකොට ඩිෆෙක්ට්ස් පේන්නේ නැහැ අපිට අනිත් මිනිස්සුගේ. ඩිෆෙක්ට්ස් වලින් වෙන්නේ නැහැ. ඔක්කොම වල වෙන්නේ ලස්සන දේවල් විතර වෙන්නේ. හරි. එකට ඉන්නකොට මොකද වෙන්නේ? ළඟට උඟ කාවට පස්සේ අවුරුදු දින ඩිෆෙක්ට්ස් එක ඔක්කොම පේන්න පටන් ගන්නවා. එතනින් පස්සේ ඇට්‍රැක්ෂන් එක කෙලින්ම රිපල්ෂන් තමයි. එක්ක මේ මිනිස්සු උදේට මූණ හොදන්නේ නැහැ. දත්ම දින්නේ නැහැ. හරිද? ඉතින් ඔය තමයි ඉතින් හරි. ෆුල් අවුල් ඉතින්. හරිද? එතකොට නේද? ගන්ධසාර ඉන්න වෙලාවයි කෙලිම රිපෙල් වෙනවා තමයි. ඒක සාමාන්‍ය කියන්නේ ඒක තමයි ළමයි කෙලින්ම මේ ඇට්‍රැක්ට් වුණාට කමන්නේ නැහැ. too much attract වෙන්න එපා. too much close වෙන්න එපා. close වුණාට කමන්නේ නැහැ. when you are with some distance definitely attraction will occur because you see all the beautiful things there. But when you get closer than some stage, right, definitely repulsions will occur. අනිවාර්යෙන් රිපෙල් වෙනවා. ඉතින් too much attract වෙන්න එපා. too much close වෙන්න එපා කියලා තමයි කියන්නේ. හරි. right. එතකොට ඕක තමයි සාමාන්‍ය කතාව. ඉතින් සාමාන්‍ය මිනිස්සුන්ට අදාළ කතාව. සහ මේ ඕක ඉතින් molecules වලත් එහෙමම අදාළයි තමයි. right. So at low pressures, that means the concentration is low. That means particles are a bit away from each other like this. Particles are a bit away from each other. So the attractions, the attractions will more pronounced. Attractions is more pronounced, right? So these will attract. These will attract. So attractions will be more pronounced. Cut to attract, you know. The attractions will be more pronounced when the particles are a bit away from each other. That is what happens with the low pressures, right? So when the attractions happen, right? When the attractions happen, right, like this. When the attractions happen, right, this volume will decrease. The volume occupied by these particles will decrease. It will shrink, right? When all the guys get attracted, the stuff will shrink. The gas will shrink. Right? Volume occupied by 1 mole of particles is now less when the attraction occurs compared to the ideal situation. So this is the real volume with attraction. This is the volume of the gas when the attractions happen. Right? Okay. So that is the idea. So this is the volume of 1 mole of gas when the attractions occur. The attractions are the ones which will predominate with the low pressures as the particles are a bit closer to each other. Why I am saying so? Because low pressures mean so Z is the Vm real over Vm ideal. So here the real value is a smaller value. Vm real is a smaller value here. When the attraction happens, Vm real is a smaller value than the Vm ideal. So this value is a smaller value, right, compared to the ideal value. Ideal value is a larger value. So it is like 1 over 2, 2 over 5. Those are 0 point values. 1 over 2 is 0.5. 2 over 5 is 0.2. Kind of 0 point values. So the Z value is now less than 1. Z value is less than 1. So if you are concerning low pressures, your Z value is less than 1 and the attraction forces predominate. Low pressures, that means concentration is low, that means intermolecular distance is high, So attractions predominate. Attractive forces predominate, right? So when that happens, Z is less than 1, right? No? Idea is clear, no? That is what happens at low pressures, right? Let's write this stuff lamai. Ab me dewa liya kamda, right? Just write. See, at low pressures, right? First write this thing. After that we can draw this one, right? Just write like this. As come to red color and write attractive forces. As attractive forces, come to the normal color, are prioritized as attractive forces are prioritized among particles, as attractive forces are prioritized among particles, the volume of 1 mole of particles of real gas, the volume of 1 mole of particles of real gas is lower compared to that of an ideal gas. The volume of 1 mole of real gas, particles of real gas, the volume of 1 mole of particles of real gas is lower compared to that of an ideal gas. Is lower compared to that of an ideal gas. Right, no? So just draw this picture and complete. Right, ne? Okay. Let's discuss about the things at high pressures. This is a situation with low pressures now. Let's discuss about the things at high pressures, right? Okay. So what happens at high pressures? At high pressures, right? Let's come up with the high pressure situations. So high pressures means high pressures means actually the concentration is high. High pressures means the concentration is high. So P is equal to CRT in is proportional to concentration. High pressures means the concentration is high. So concentration is high means you have more particles in unit volume. You have more particles, no number of moles of molecules in the unit volume, right? So that intermolecular distance is low. Intermolecular distance is low, right? Now, higher the concentration means the situation is like this. No, high concentration means you have more particles in unit volume, like this. More particles in unit volume, the high concentration situation. If you need a low concentration situation, it's like this. Low concentration situation is like this, very less particles in unit volume. Low concentration is the high concentration, right? So with a high concentration, intermolecular distance is small, right? So particles are very close to each other. Particles are very close to each other. When the particles are very close to each other, what kind of a force will more pronounced? When the guys are very close to each other, yes, those are the repulsions. Those are the repulsions. So when the particles are very close to each other in this discussion system, repulsion forces are more pronounced. Repulsive forces are more pronounced, right? So let's use that knowledge to come up with the competitive factor, right? So you are with this kind of system, right? Say if you are with ideal gases, right? So particles are very close to each other. The particles are very close to each other with ideal gases, right? So if they are ideal, no worries, no attractions, no repulsions would occur. As they are ideal, no attractions, no repulsions would occur. So this is the volume occupied by 1 mole of gas particles. Let's consider that these 5 dots represent, right, 1 mole of gas molecules, right? So that we can consider this area as the molar volume for ideal gas, if the gas behaves ideally, right? But we know now we are concerning about real gases. So if these gas molecules are real gases like this, then what will happen? These guys are very close to each other, so that repulsive forces will occur. For as real gases, the intermolecular interactions are there. So repulsive forces will more pronounced. Repel. These guys will repel from each other. So repulsions occur means kind of expansion of the gas. So with these repulsive forces, now the volume of your gas would be like this. Volume of 1 mole of gas molecules would be like this when the repulsive forces are among gas particles. So this is your molar volume of the real gas, real volume, right? So we know that Z is the Vm real over Vm ideal. When the pressure is high, the repulsive forces happens so that the molar volume of real gas is now high compared to molar volume of ideal gas. As with the repulsions, some expansion would occur with the gas molecules. So now the same 1 mole of gas molecules will occupy more space, right? So volume of real gas molecules, 1 mole of gas molecules is greater than the volume of 1 mole of ideal gas molecules, right? So this value is kind of a larger value. This value is kind of a smaller value. So it's like 2 over 1, just 2. 5 over 2, 2.5. Like those values are some values greater than 1. So the Z value would be greater than 1. Right? When the repulsive forces are happening, Z value would be greater than 1. Such forces appear when your pressure is high. When your pressure is high. The thing is clear? No? Right. Let's write this stuff. Right? Okay. At high pressures. At high pressures. Let's write. When gas molecules are closer to each other, so high pressures means high concentration, right? Then the gas molecules are very close to each other, as you are with more population in a unit volume, right? Okay. When gas molecules are more closer to each other, the electron clouds of gas molecules, get more closer, and the electron clouds of gas molecules get more closer, and then the come to red color, repulsive forces, then the repulsive forces come to the normal color, get prioritized among gas molecules, get prioritized among gas molecules. At the next line, right? Just write at the next line. So the volume of within brackets, the space occupied by, within brackets, space occupied by, close the brackets, 1 mole of gas particles, 1 mole of gas particles of real gas, 1 mole of gas particles of real gas will be higher to that of an ideal gas, right? So you can draw this picture, draw this one and this stuff as well as this, right? Let's complete the note. right නේ ළමයි. හරි. අපි එහෙනම් ඊළඟ කතාවට යමු. Right? So let's use the knowledge we have gathered to read kind of a compressive vector curve. Compressive vector curve එකක් අපි read කරන්න අපි මේ knowledge එක use කරමු. Right? Okay. See the next step. Right, we are going to read to learn how to read a compressive vector curve, right? This curve is appearing in your resource book, Lamai. Okay, let's try to read this one properly. In this axis, you have the Z, the compressive factor, is equal to PVMORT. At this axis, it is the pressure, right? ATM pressure, right? So compressive factor is always greater than 0, right? It's always a positive value, right? Compressive factor is always a positive value, right? So it is Vm real over Vm ideal, no? The molar volume can't be 0, no? Right? So Vm real is a positive value, Vm ideal is also a positive value, right? So positive divided by a positive value is definitely a positive value. So the compressive factor is always greater than 0, right? Okay. So here the 0, it is always greater than 0, right? No negative values for the compressive factor. Remember that, right? Okay. And where are the ideal gases? Are there. So this is the ideal situation, right? This is how you represent the ideal gases, right? With the compressive factor 1. The compressive factor 1, you come up with the ideal gases, right? So actually this explains the short and sweet description of an ideal gas. Did you remember the short and sweet description of the ideal gas? So we have two methods, two descriptions to define ideal gases in a way syllabus. Two descriptions. What are the two descriptions? Have you remembered? Right, on the on any point of this line, that PV is equal to nRT, right? Is it is equal to PVM or RT? This is one means PVM is equal to RT. PVM is equal to RT, right? This one means PVM is equal to RT. That is what happens with the ideal gases, right? PVM is equal to RT means PV is equal to nRT, right? In V over N, no. Vm means that, no? So PV is equal to nRT, right? Okay, so on any point of this line, this is equals one line, the PV is equal to nRT, right? Actually, this thing explains what I have already told is actually this thing will explain the second description or the short and sweet description of the ideal gas. What is that? So the short and sweet description of the ideal gas, what we have learned with the first day's lesson, is actually the ideal gases are the gases which follows the P equals nRT at any temperature and pressure. At any temperature and pressure, right? That is the short and sweet description of an ideal gas. Any gas following the PV equals nRT or the ideal gas law under any temperature and pressure situation. Under any temperature and pressure situation. So you clearly see with any pressure, any kind of a pressure, for ideal gases, the PV is equal to nRT. For ideal gases, the points, right, on this is a equals one line. So for ideal gases, for any pressure, this is equal to 1. That means for any pressure, the PV is equal to nRT. Right? So that is the ideal line of this compressive vector curve. Right? So let's come up with the real gases now. Let's try to draw the real gases in this curve, right? So when it comes to real gases, right, normally real gases follow this kind of range with curves, right? This kind of a trend. So starting with z is equal to 1, because starting with you have to start with this number. Why is that? Because at the pressure 0, at the very low pressures, all the gases tends to behave ideally. All the gases tends to behave ideally. We started our discussion today with that, with very low pressures and very high temperatures. With very low pressures and very high temperatures, all the gases tends to behave ideally, right? So at very low pressures like this, when the pressure is equal to almost 0, right, particles are very far away from each other, very far away from each other. The particles won't feel the existence of the other particles, so no interactions there. Attraction and repulsions hard to occur, no interactions, because the particles won't feel the presence of other guys at very high distances among particles. That is what happens with the 0 pressure. So it tends to behave ideally, right? So any gas starting from here at the pressure equals 0, those are ideal, right? So normal gases are following this kind of a curve, and you clearly see when the particles become more closer than the ideal situation, when the particles become more closer, first the attractive forces predominate. Attractive forces predominate. That is what we see until here, until this point. That is what we see. Attractive forces predominate, right? So Z is less than 1. Z is less than 1 means attractive forces, right? Z less than 1 means attractive forces. Right? Attractive forces. Right? So Z is greater than 1 means repulsive forces. Right now? So any gas, normal gases, right, tends to do some attractive forces with low pressures. When the pressure is low, attractions will predominate. That is what happens. Attractive forces will increase. That means this Z becomes much lower than 1. Attractive forces. But after some point, when the particles get much closer to each other, the repulsions tends to occur. So that repulsive forces will increase. Ultimately, from here onwards, the repulsions are the most predominated forces. Right now? So attractive forces increases up to here. From here onwards, repulsion starts to occur. So that after this thing, only the repulsions will occur. Right now? So this is the normal nature of a curve for a real gas. Let's say this is for the carbon monoxide. Let's consider some other real gases. The carbon tetra, right, hydride, that means CH4. CH4 gas is like this. Some curve for CH4 that is also following the same trend, right? Depth of the thing, no? Right? And these are the normal curves, and we see some special guys. The H2 and the helium, those two curves are very special. These are the normal real gases, right? But helium and H2 are special ones, right? So helium is the gas which is closest to the ideal behavior. Helium is the gas which is closest to the ideal behavior, right? Okay, which is closest to the ideal behavior. Why is that? Helium is kind of a noble gas, you know. There is no bond formation there. So noble gases are the ones which are the closest to the ideal behavior, right? Less interactions, right? So out of those noble gases, helium is the best one, because helium is the smallest noble gas. So among mobile gases, only the London forces would occur. No? Mobile gases are real gases, right? London forces would occur. No? So the London forces are minimum when the size is small. London forces are minimum when the size is small. That is what happens with the helium. So the minimum London force with helium. So the helium is the closest to the ideal behavior, right? Okay. So when it comes to helium gas, right, most of the pressure, it will follow the ideal line like this. Through most of the pressure values, it will follow the ideal line like this. After that, very slight increasement. Very slight increasement. This is what helium do. The closest to the ideal behavior, closest to the ideal line, Z is equal to 1. Right? Okay. That is a special one, helium. Right? Then the hydrogen's curve. Hydrogen normally comes like this. The curve of the hydrogen. All the things will start with Z is equal to 1, right? It's the curve of the hydrogen. So these two guys are special. Right? These two guys are special. Normal gases follow this kind of routine. First the attractions, then the repulsions. And another curve is there in Norris's book. That is the curve of the ammonia. That is also some kind of special stuff. Curve of ammonia. This is the curve of ammonia. And stops at this stage. Right? So is the CH4, the carbon monoxide, right? So what happened to here? What happened to ammonia here? Basically, when you are increasing the pressure, its attractive forces increases, no? Attractive forces increases, no? When the pressure is increased, right? Attractive forces will increase up to some extent. Attractive forces will increase, no? Right? Here you would observe the maximum attractive forces. Here you would observe the maximum attractive forces at the depth of the curve, right? At that point, what happens is actually the NH3 gas starts to liquidize. NH3 gas starts to liquidize. When you increase the attractive forces, what will happen? The intermolecular attractive forces will increase, so that ultimately here with the NH3 it has liquidized, turned to a liquid. The gas turned to a liquid. After you convert it to a liquid, you can't apply any equation with R. If it is a liquid, you can't apply any equation with R. R is a universal gas constant, right? So after this pressure, the chemical fact is not defined. After this pressure, chemical fact is not defined for the NH3 as it is converted to a liquid. Right? That is why the NH3 curve stopped at this point. Right? These are the few curves appearing in the resource book, so you should know about these ones. And another important stuff to mention here is basically from the depth of the curve, from the depth of the curve, actually you can comment on the intermolecular attractive force strength of these species. Intermolecular attractive force strength of these species can be discussed with the depth of the curve. Right? When following these curves, you clearly see the most attractive forces should appear with the NH3 as depth is highest with the NH3, because going towards down, right, attractive forces increases, right? The attractive forces are maximum with the NH3. Then with the CH4 and these with the CO out of these three guys, right? So we can write that thing as well, right? Intermolecular attractions. Or intermolecular attractive forces, or attraction strength, let's say. And concerning this, the NH3 is the maximum. and we know actually this is because of presence of hydrogen bonding, right? Presence of hydrogen bonding. That is also confirmed here, right? So if you look at this thing, so intermolecular attraction forces of CH4 is greater than the carbon monoxide, right? It's a very special thing to observe from this curve, which is appearing in the resource book, right? Okay, according to this curve, the attraction strength of CH4 is greater than carbon monoxide. It's a very special situation, right? Because with the knowledge of the unit 2, right? With the knowledge of the unit 2, right? You won't get that idea, because one may think this is a polar molecule, so that dipole-dipole interaction would occur. These are non-polar molecules, so that London forces should occur, right? Dipole-dipole are stronger than London, right? So one may think that this guy should be with a greater intermolecular attractive forces, but that is not happens here. That is not the practical situation, right? This is a practical curve obtained. It says the intermolecular interaction forces of CH4 is greater than carbon monoxide, right? Clear? So even with a smaller weight, this guy is the greater weight, right? So, but this curve says that CH4 is with a greater intermolecular interaction forces than carbon monoxide, right? Actually, that happens because of right because of that asymmetric nature of CH4 molecules with the molecular vibrations, right? With the temperature appearing, it's considering temperatures, right? Let's say this is the 300 Kelvin situation, room temperature situation, right? So with the temperature appearing, right, CH4 molecules are not symmetric, right? Even though you think that CH4 is kind of symmetric molecule like this, that is not the case. With the temperature, the molecular vibrations occur. So these bonds will vibrate, stretching vibrations, stretching modes, so that instantaneous dipoles would occur. Instantaneous dipoles would occur, right? So that this will create some London forces. That London forces are very heavy compared to the forces of the carbon monoxide, because with the carbon monoxide it is referred to as a rigid molecule. The molecular vibrations are very limited with the triple bond, so it's a rigid molecule. So compared to the dipole nature of this thing, this guy's induced dipole is more heavier, because very weak bonds and more stretching vibrations will occur, so that the molecules will, the symmetry of the molecule becomes asymmetric easily. So this guy's polarizability is high, right? That is what happened there. So that CH4 is with a very strong London forces compared to carbon monoxide in this case, right? That is a practical situation. So you can check that even with the boiling points. So boiling point of CH4 is greater than carbon monoxide. You can check that through internet, right? So the boiling point variation also follows this kind of a trend, right? So one can see the boiling point variation, right? Right? So in the boiling point variation, also follows that trend, same trend. Right? So this situation with hydrogen bonds, right? This is London, right? Even though this is dipole, that special thing occurs, right? Okay. So just complete this stuff, Lama. Just complete this stuff. Right, this is a rigid molecule, right? Polarization is with low. Okay, so let's complete this stuff. Right. So another point to grab from this one, Lamai. So that thing is actually you can clearly see normal gases, right, behave according to P equals nRT, right, two occasions. Let's consider this CH4 kind of a gas. So if you are regarding the CH4 kind of gas, that's normal gas, right? Not these special ones, not these special ones. But if you are thinking of a normal gas, right, like CH4 or carbon monoxide, they are that CH4 will follow the PV equals nRT. The PV is equal to nRT for CH4 at this point as well as at this point, at this point as well as at this point. Right? Actually, this point clearly indicating the ideal behavior with almost zero pressure. It clearly indicating the ideal behavior, right? And at this point, even though the CH4 follows the P equals nRT, the gas is not ideal, right? Gas is not ideal, right? Why is that? At this point, both the attractions and repulsions are there with equal strengths. With equal strengths. That is the idea, right? At this point, you don't have attractions or repulsions. That is the ideal behavior for CH4. But at this point, even though it follows P equals nRT, it is not ideal. The reason is here both the attractive and repulsive forces are there, and the special thing there is those are with equal strengths, so that no net attractions, no repulsions, no net attractions or repulsions. That is why PV is going to be equal to nRT. But it is not ideal, right? Both the attractive and repulsive forces are there, so that this situation is not ideal, right? Only at the very low pressures you achieve the ideal situation, not at high pressures. Right now, the thing is clear, right? Okay, that is all about the concept of kind of gas, how it affects the chemistry factor, right? Next thing we are going to discuss is the effect of temperature towards the chemistry factor. The effect of temperature towards the chemistry factor. Let's discuss about that thing, right? Okay. Right. temperature of the gas. Let's discuss how this temperature will affect the chemistry vector, right? So this is going to be this is equals one line, right? Okay, that is your ideal gas, right? And any point on this line is actually following the P equals nRT. Right now, okay. So I'll draw few curves regarding the same gas but with different temperatures, and I suppose you to write comment on that thing, which curve belongs to which temperature. That is our exercise now, right? So let's consider some same gas, CH4 gas, with different temperatures. So I'll draw a few curves, right? I'll draw a few. Right. So, okay. So I've drawn few curves, right? I'll label these things A, B, C. And this is A, this is A, B, C. Right. Let's assume these three curves representing three temperatures, right? 300, 500 and 1000 Kelvin. So my question is, which curve representing the 1000 Kelvin? What is the curve representing the 1000 Kelvin? Yes, it is the curve C. It is the curve C. So C is the curve which represents the 1000 Kelvin out of 1000, 500 and 300. So this is the 500 Kelvin curve. This is the 300 Kelvin curve. How come? How to decide that? It's like this, Lama. So the point is this: you are not expected to by heart these things, right? I'll give you the theory. Right? The theory is this: when the temperature is very high, the kinetic energies are high. When the temperature is high, that means kinetic energies are high. When the kinetic energies are high, less interaction time for particles to interact. When the kinetic energies are high, the molecules are moving very speedily, very fast movements among molecules. So less interaction time for molecules to interact. That means attraction forces as well as repulsion forces will decrease, as very less interaction time for molecule to interact. Attractive forces as well as repulsive forces will decrease. So you see, your curve should appear very close to the ideal line then. The attractive forces are minimum as well as the repulsive forces are minimum. So that the greatest temperature should be the one which is more closest to the ideal line. The curve representing the greatest temperature should be the curve which is more closest to the ideal line. Less attractive forces, less repulsive forces, right? So that is that, no? So from 1 onwards you have the repulsive forces, down you have the attractive force one. Right. So when the temperature becomes greater, your curve will become more closer to the ideal line. That is the idea. Right? Okay. When the temperature is very smaller, your curve is deviating more from the ideal line. Right now? The idea is clear now? So this is your 300 Kelvin situation, deviating more from the ideal line. This is 500. This is the 1000 Kelvin. More the temperature, smaller will be the attractive forces as well as repulsive forces, as very limited interaction time is available with the greater temperatures, as the kinetic energies are very high there and molecules are traveling with very high speeds. Right? The idea is clear? So first write this stuff lamai මුලින් අපි ලියා ගමු ලියලා ඉවරලා මේ pitch එක දාගමු. Right? හරි. Let's write this thing. Right? So at higher temperatures, right? That thing is there no? At high temperatures, right? So like write that, right? At high temperatures. At high temperatures, just write. As kinetic energies of gas particles are very high, as kinetic energies of gas particles are very high, as kinetic energies of gas particles are very high, at high temperatures, as kinetic energies of gas particles are very high, the tendency slash ability to have intermolecular forces, the tendency slash ability to have intermolecular forces, within brackets, attractive as well as repulsive forces, within brackets, attractive as well as repulsive forces, attractive as well as repulsive forces, close the brackets, become weaker. So come to the red color and write lamai. Come to red color and write. In the next line it is better to write. At the next line, come to red color and write. The curves would be more closer to z equals 1, more closer to z equals 1, the curves would be more closer to z equals 1, within brackets, ideal behavior, close the brackets, when temperatures are high, when temperatures are high, right now. Right. So you can draw this one. So complete this note now. Draw this one. This is for one considering gas with different temperatures. How the combustion factor varies, right? Okay, just complete. Right. So this is all about, you should know about the real gases, about the compressive factor. Now let's move towards the next topic under the real gases, that is Van der Waals equation. Van der Waals equation, right? So with this, you clearly see with the compressive factor, you have studied that for compressive factor, for real gases, PV is not going to be equal to nRT with most of the equations. Only two occasions are there when the PV is going to be equal to nRT, that is at this point as well as one of these points, right? So, but all the other occasions, PV is not going to be equal to nRT for real gases, right? So, we have to come up with another new equation which could be applied for real gases, right? That is actually referred to as the Van der Waals equation, right? Let's start the discussion about the Van der Waals equation, right? Okay. Right. So Van der Waals equation. Right. So the interaction is given, right? The interaction is actually, we know that for real gases, right, the PV is not going to be equal to nRT, right? The reason is that what? Because with normal pressures and temperatures, right, they have intermolecular attractions as well as repulsions among gas particles. So it is not the ideal behavior, and the volume of real gas molecules can't be neglected compared to the volume of the vessel. Because of those two facts, real gas is not following the ideal behavior. That means they are not following the Pavicus nRT, right? Okay, so that we have to come up with some corrections for the pressure and the volume to equalize that multiplication to the nRT, right? So the point is this now. So for real gases, right, the PV is not equal to nRT, right? So if we can do some corrections for P and V, some corrections, pressure with a correction, right, and volume with a correction, so some added value or some deducted value, then we would be able to equalize that multiplication to nRT. Then we would be able to equalize that multiplication to nRT, right? So this is what we are doing, right? Coming up with some corrections for pressure and volume, right? That is what we are doing with the Van der Waals equation, right? So as this is not equal to nRT, we are going to do some changes for the observed value of pressure as well as to this thing, right, to the observed value of volume. We are going to do some changes, some corrections, then we would be able to equalize that multiplication to nRT, right? That is what we are doing here as the Van der Waals equation, right? So first of all, let's discuss about the pressure correction. Right? Let's discuss about the pressure correction, the need of that, and the correction. Right? So the first thing is the pressure correction. Right? Pressure correction. Right. The idea is this. When concerning these normal pressures, right? So normal pressures means 1 atm situations, right? When concerning 1 atm situations, right? Among real gas molecules, attraction forces are there. We know among real gas molecules, attraction and repulsion forces could occur. When considering the normal pressures, 1 atm kind of normal day-to-day pressures, the attraction forces are the ones which predominate among real gas molecules, because normal pressures means the particles are not that much closer to see some greater repulsions. 1 atm is normal pressure. If you are thinking of 2000, 3000, kind of 5000 atm, then such pressures are very high. The repulsions would occur among particles. But with 1 atm pressure, which is a pressure which is not equal to 0, but a smaller value. Pressure not equal to 0, but a smaller value. Then attractive forces are the prioritized kind of forces, right? So let's compare the ideal situation and the real gas situation at those normal pressures. So if you think of kind of a ideal gas and a real gas, right? So this is the ideal gas, this is real gas. I'm going to draw, right? So if you are an ideal gas, right, the particles would appear like this, right? If you are real gas, the particles are much larger. I'm going to draw the same 5 particles, right? Right? This is the real gas situation, this is the ideal gas situation, right? So when it comes to ideal gas, among particles, right, no intermolecular forces. No intermolecular forces. So the pressure exerted on particles are like this, right? So pressure exerted on particles are due to the collisions of these particles with the walls. So when this guy hit the walls of the container, right, that force divided by the total area, right, FOA will give you the pressure, right? Okay, that's how the pressure will arise with the ideal gas system. So we'll write that pressure as pressure of the ideal system, pressure of ideal, right? That was the pressure which equalized the PV because nRT, which equalized the PV multiplication to the nRT. If you had used this pressure, right, the PV multiplication will be equal to nRT, right? But when it comes to real gases, we know at these low pressures, the attractive forces predominate. Attractive forces predominate. So that then what will happen? So this molecule, I am considering this same molecule. This will attract. This will attract towards other particles like this. This will attract towards other particles, so that this molecule will drag by the other particles like that. Drag by the other particles. That will attract to other particles means, in another way, one can say it will be dragged by the other particles. So the force exerted on walls by that particles becomes lesser, because due to this drag by the other particles. With the drag of the other particles like this, as the attractive forces are there among particles, now the force exerted on walls from these particles becomes less now. So with a smaller speed that will collide with the walls because of backtrack by the other particles because of the appearance of the attractive forces. So less amount of force will be inserted in the walls. That means less pressure will arise with that. So this is the pressure. This is the measured pressure. That is all about the measured pressure of the real gas. And you clearly see this value will be a higher value and this value will be a lower value because of this backtrack. Right? The idea is clear. So we can say that P ideal is actually greater than the real gas pressure, the observed pressure of the real gas. Right? So if you need to equalize this pressure, if you need to equalize this real gas pressure to the ideal value, you need to add some value. You need to add some value to here to equalize the thing. හරි. දැන් මෙතන value එක ළමයි වැඩි. මෙතන value එක අඩුයි. right? නිකන් හිතන්නකො මෙතන value එක 5යි කියලා. මෙතන 2යි කියලා. එහෙනම් හරි. මේ පැත්ත සම්මෙමි. දෙක තියෙන term එකේ තියෙන පැත්ත සමාන කරන්නම් 5ට. ඔයාලට තව value එකක් එකතු කරන්න වෙනවා. Right? You have to add some value to the observed pressure with the real gas. You have to add some value to the observed pressure with the real gas to equalize that value to the value of the ideal gas. Right? So if you are applying the value of the ideal gas, then only the PV multiplication will be equal to the nRT, right? So what we need to do is we have to equalize somehow by adding or deducing or by any kind of a mathematical operation. We have to equalize the observed value of the real gas to the ideal gas value, right? Then only we would be able to get some equal sign with the PV term and the nRT term, right? So that we have to add some value to the observed value with the real gas to equalize that part to the number of the ideal gas, pressure of the ideal gas, right? So this added value is found to be like this: a n squared over v squared. This was the practically observed value which they have added, right? You have to add some value, right? So what are these terms? What are these terms? N and V carrying the normal meanings, right? N means number of moles of the real gas and V is the volume of the vessel. That's what terms are there. And A, what this A means? This A is a van der Waals constant which is related to the attractive forces, right? A is a van der Waals constant related to the attractive forces. And remember, this is independent of temperature and pressure, right? Right? Greater the attractive forces, greater will be the attractive forces, greater will be the right? Is proportional to intermolecular attraction strength. Right? If you need an example, the A value of H2O is greater than the A value of, right? Let's say CO2 or something, like CO2. So you know, among H2O molecules, hydrogen bonds are there. Among CO2 molecules is the London forces, right? So you clearly know that hydrogen bonds are stronger than London forces, right? And the attractive forces are greater, A value will be greater. That is very understood, lamai. Then attractive forces greater means, right? Attractive forces greater means, right? The particles will hit the walls with very low force. When the attractive forces are stronger means the backtrack will be stronger felt by these particles, so that they will hit the walls with very smaller force, right? So that pressure will be very low. When the attractive forces are greater, pressure will be low. Pressure will be low means you have to add some greater value to equalize the value to this value. To equalize the value to this value, you have to add some greater value. So the greater value can be provided by this A term. That is how this value will be increased by increasing the A. So when the attractive forces are greater, the A value should be a larger value. That is what it says, right? Okay, then? Right. I think so. You can complete this stuff, right? So just complete them. Before complete now, just we'll write the stuff, right? අපි මුලින් ලියාගනිමු. ලියලා ඉවර වෙලා මේක complete කරමු, right? හරි. So just write this stuff, right? ඒක ලියමු ළමයි මුලින් ඊට පස්සේ අපි අඳගන්න පුළුවන්, right? That's right. Right, put a dash on right. Put the first dash on right. At normal pressures, within brackets, example 1 into 10 power 5 pascals. Within brackets, example 1 into 10 power 5 pascals. 180 again. Close brackets. Molecules of gases are close to each other, somewhat close to each other, like that. Somewhat close to each other. Molecules of gases are somewhat close to each other, and molecular interactions within brackets attractive forces, molecular interactions within brackets attractive forces, close brackets, starts to operate. Next dash, dash දාලා Therefore, at these pressures, molecules cannot strike on walls. Molecules cannot strike on walls of the container. Molecules cannot strike on walls of the container with full force of impact. As they are dragged back by the other molecules, due to the presence of molecular attractive forces. Come to the next line now. Come to the normal color again. Thus. Come to red color again. pressure exerted by the real gas, pressure exerted by the real gas is lower than the pressure exerted by the real gas is lower than the pressure exerted by the ideal gas. Pressure exerted by the ideal gas. Pressure exerted by the real gas is lower than the pressure exerted by the ideal gas under similar conditions. Under similar conditions. Right? So just complete this stuff. Complete. Right නේ ළමයි. හරි. අපි ඊට පස්සේ කතා කරනවා pressure correction එක ගැන. right ළමයි දැන් ඉතින් මේ value එක දැම්ම නම් ඔයාගේ nRT එක right pressure විදිහට මේ value එක ඔයා use කරා නම් for a real gas you could be think of equalizing the PV term to the nRT, right? Okay, right. Let's discuss about the volume correction now. Right, volume correction. Right, the idea is Islam. So if we are concerning, if you are concerned an ideal gas and a real gas, right? Okay, so this is the ideal gas, right? This ideal gas, right? This is real gas. Actually, ideal gas molecules are with negligible volume. Ideal gas molecules are with kind of negligible volume. But real gas stuff are with some considerable volume. If the same molecules are appearing as real gas, come with some considerable volume. Right? So actually, what is that V? What is that V appearing in the PQS NRT? So normally, the V appearing in the PQS NRT, right? Normally we have applied the volume of the vessel. Volume of the vessel, right? That is what we have applied in doing the calculations. But that volume of the vessel there is actually equal to the volume of the free space available for ideal gas molecules to move. Yeah, the P, because in RT, we had used the volume of the vessel as V of the P equals in RT. But actually that V is the volume available or the free space available for ideal gas molecules to move. Right? So it is referred to as the ideal volume or the effective volume. So if you are to think of effective volume here, effective volume. If you think of the effective volume or the ideal volume, it is actually, right, the volume available for ideal gas molecules to move. That is equal to V, volume of the vessel. That is equal to V, the volume of the vessel. Actually, for the P equals NRT, we have to substitute this effective volume, right? The volume available for your gas molecules to move, right? The volume available for your gas molecules to freely move, right? But when it comes to a real gas, what about the effective volume? Volume available for real gas to move is also known as the ideal volume. Now, that volume is less than the volume of the container. That volume is less than the volume of the container. Volume of the container is the measured volume, right? That volume, the effective volume, is less than that value. I'll write it less than that value, right? I'll put it as X, right? The volume available for these gas molecules to freely move is less than the volume of the container. This is the volume of the container. But here it was equal to the volume of the container. Why is that? Because the space occupied by the ideal gas molecules is negligible. අර මේ molecules කිසිම space එකක් obtain කරමු නැති නිසා මේකට available space එක move වෙන්නත් is equal to V. But here real gas molecules take some space of your vessel. So that the free space available to move these gas molecules is less than the volume of the vessel, less than the B, which is the volume of the vessel, less than the calculated volume, right? Okay. So that value, they had measured that, experimentally shown that that value is equal to NB. That value is equal to NB, right? What is NB? N is the number of moles of gas particles there, and B is the volume of 1 mole of gas particles. Volume of 1 mole of gas particles into number of moles will give you the total volume occupied by the gas particles. B is the volume of 1 mole of gas particles. N is the number of moles there. So number of moles into volume of 1 mole of gas particles will give you the total volume occupied by the or taken by the gas molecules. You have to deduct that value from the value of the vessel to come up with the free space available for moving those particles. Right now, got the idea? So here NB is the total volume occupied by the molecules themselves. Occupied or taken by the molecules themselves. Right? And the B is volume of 1 mole of gas molecules. Right? I'll write it here. B is a van der Waals constant which represents the volume of mole of gas molecules. Right? Actually, this B value is proportional to molecular size. This B value is proportional to molecular size. Larger you are, right, larger space it will take by the 1 mole of gas molecules. Right? If you need an example, right, the B of H2O is smaller than the B of CO2. B of H2O is smaller than B of CO2. So normal lamai molecular size, right, can be, I mean, you can think of molecular size as a measure of its molecular weight. Greater the molecular weight, that means you have more nuclear particles, more protons in your nucleus. That means more electrons will be there. That means more number of electron shells would appear. That means your size will be high. So greater the molecular weight, that means the size will be high. So it's kind of a measure of molecular weight, the size, right? So molecular weight is 18 here, it's 44. So this should have a should occupy, take some greater space, right, compared to this one, right? So that is the idea. So we need to substitute this value as the volume, right, of that equation to equalize the pressure volume term to nRT, right? So when the pressure volume term equals to nRT, right, there the volume is actually the effective volume, the volume which is available for gas molecules to freely move, right? That is the volume should be applied there, right? So we have to apply this value. So if you are to apply that pressure value, that P plus AN squared over V squared with this value, then your nRT term will be equal to that PV term, right now? Okay, so let's write the things and then we can copy this stuff, right? Just write first of all like this, the volume correction. At normal pressures, example 1 in 10 power 5 pascals, example 1 in 10 power 5 pascals, comma, molecules are close to each other, molecules are close to each other. Molecules are close to each other. Within brackets, compared to ideal behavior. Sorry, compared to ideal solution, ideal situation, compared to ideal situation. Close the brackets. Come to the next line and write. Come to the next line and write. So a significant volume of the container, is occupied by gas molecules. Is occupied, or one can say is taken, is occupied within brackets taken close brackets by gas molecules. Next line, come to the next line and write. So come to red color and write. Satu panel liana. Continue kan statement satu panel. The ideal volume within brackets, the free space available for molecules to move, close brackets, is less than the measured volume within brackets, volume of the vessel. Close brackets. Come to the normal color. At the next line you can write because again in red color, instead of moving in volume V, these molecules are now restricted to an effective volume of these molecules are now restricted to an effective volume of within brackets B minus NB. Right now. So you can copy this board, right? This is the ideal gas. It's the real gas, right? So just copy this one. right නේ ළමයි. හරි. ඉතින් ළමයි ඔය විදිහට අපි හොයාගත්ත මේ අපි කරපු corrections දෙක. volume correction එකයි pressure correction එකයි. We can apply those volume correction and pressure correction, right? And if you apply those two things, right? Let's come up with that. Right? So for ideal gases, we had written it like P V is equal to nRT. So if you have to apply the ideal thing, the PV term will equals to nRT, right? So when it comes to real gases, so now we had done some corrections. The P ideal is equal to pressure of the measured real gas plus A n squared over V squared, right? The volume, the pressure correction. And the volume of ideal is equal to measured volume of the real gas, that means the vessel volume of the vessel minus NB. We have to deduct some value as the real gas molecules occupy some space. When that corrections have been applied, the thing will equal to nRT, right? So this equation of state is referred to as the Van der Waals equation. Is referred to as the Van der Waals equation. This is referred to as the Van der Waals equation. I'll write it here. Right. So concerning 1 mole of particles, concerning 1 mole of molecules, you can simplify the Van der Waals equation like P plus per 1 mole, that means N is equal to 1. 1 squared is just 1. So that A over V squared. So in disappears now, 1 squared is 1. V minus N is 1. So 1 into B is just B is equal to N is 1, that means 1 RT, that is RT. So Van der Waals equation can be written like this as well. Both forms are acceptable as Van der Waals equation. Or one can write the Van der Waals equation, right, like this as well. P plus X to the pressure, you have to add something, and V minus Y to the volume, you have to do some correction by deducting some value, is nRT. Like this also, you can represent the Van der Waals equation. All the forms are okay as Van der Waals equation, right? This is the best way. Or by considering 1 mole, you can write the same thing as this. Or as a simplified form, you can come up with the Van der Waals equation like this as well. The X is the pressure correction, Y is the volume correction there, right? So let's go to the note there. Your note is with these things, right? See, it says having taken into account the corrections of pressure, right, and volume, we can write the equation PV is equal to nRT as P plus A n squared V, this thing, right, nRT. This equation is called the Van der Waals equation. A and B are Van der Waals constants. This is the Van der Waals constant related to the interval attractions, and this is Van der Waals constant related to the size of the molecules, right? A and B are Van der Waals constants per mole of molecules. When A is equal to 1, you can come up with this thing as well, right? And keep that in mind, Lamai. This Van der Waals equation can be applied for the ideal gases as well, right? You can apply the Van der Waals equation for ideal gases as well, right? even though we derived this thing for real gases, this can be applied for ideal gases as well. When ideal gases are concerned, this A term becomes 0 as well as B term becomes 0. With ideal gases, no intermolecular attractions or repulsions. So attraction strength is 0. So when this is 0, this term disappears. P, only P appears. With ideal gases, right, no size with gas molecules, point masses, size is negligible. So B is 0. B0 means this term disappears. So both of these terms disappear when we are applying these two ideal gases as A and B are 0. So that P is V is equal to nRT, right? So that we can apply the Van der Waals equation for the ideal gases as well. So Van der Waals equation can be applied for any gas, ideal gas as well as real gas. But the ideal gas equation is only giving you the accurate values for ideal gases only, not for the real gases. Right now, that is the idea. So this is all for today. Right? Today we have discussed about the two major topics under real gases. First, the compressive factor. Now we had completed the decision of the Van der Waals equation. Right? Another thing is to study, and we'll do that thing at the next class. That is all about the liquefaction of gases. Right? How the gas will be liquefied by applying pressure. We will be discuss that thing at the next class, and we are supposed to complete this lesson at the next class, right? Okay, so then we'll stop at here. We'll meet at the next class. Until then, goodbye.